and welcome to 22.4, which is Series and Parallel Concepts. Today we're going to be talking about how to hook things up electrically as they get more complicated. Hooking up multiple devices to the same voltage source. There are ways to do that. A couple different ways. One is called series and the other one's called parallel. And I just found this graphic online to show you right now the short difference. We're going to talk today about what's similar to these and what's different. Why you would hook something up in series versus why you want to hook something up in parallel. The pros and cons of each. I have a couple of metaphors to kind of explain why. And specifically with voltage and current. How is voltage related in this one? How is current? How does current work? How does voltage work in a parallel? How does current work in a parallel? We're going to talk about both of those for both of these different types of circuits. So let's get started. Maybe you saw a couple of the relationships as you were doing this activity where we built a series circuit and I had you take current readings everywhere. You noticed that the current was the same everywhere. Let's go over. I got a series circuit that's built right here. Pulling out my ammeter. A series circuit is whenever you hook something up kind of like a train. There's only one pathway. You'll look here, there's only one path, one road for this current, and you're forced to go through every single one of your loads. So because there's only one road, the current is going to be the same everywhere. 0.5 amps, 0.5. Everywhere I'm going to insert this meter, I'm going to get 0.5 amps everywhere. So that's number one. That's an essential understanding, number one. And we're going to throw that into our notes. Series circuit. A circuit where there is only one pathway for the current. I have here kind of a metaphor for what a series circuit is. So this is kind of an overhead view of traffic. If there was a blockage of traffic, which this red car is the thing that causes, you watch this red car, it swerves unexpectedly, and it slows down this car, and it just kind of cascades back throughout traffic, so everybody slows down. And the same thing is true inside of a series circuit. Like when I have current, if I increase the resistance here, you're going to see that it slows down the current everywhere. So I'm going to increase this to, as this goes up, now I go up to like, let's say 50. The current has gone down to 0.21. It was 0.5 before. But the more and more current that you have, the more and more resistance that you have, I'm squeezing the pipe. Like this was, imagine this as a water pipe. If I squeeze anywhere, it's going to slow down the water everywhere. And that's a big idea. Current is the same everywhere. No matter where you have in a series circuit, the current is the same everywhere. And you can see over here, this is kind of a little animated GIF of a series circuit, that if you cut off the current or if you disconnect your circuit anywhere, that's going to stop the current everywhere. So going back here, turn her back to, I think it was 10. If I open this circuit, if I cut this right there, nothing. There's no completed circuit anywhere. There's no pathway for the electrons to go from the negative around to the positive. So I'm stuck. So breaking one of these light bulbs, right, like taking any one of these out, if it burns out or whatever, then you don't have a circuit anymore. Next idea, let's talk about voltage. Voltage is like pressure. So I have a hose that's right here, and this hose is a singular long hose, and I had three people, and I said, each of you squeeze that hose. Somebody is squeezing the hose a little tiny bit. The next person is squeezing the hose a lot. They're really squeezing it hard. And then the third person is kind of in the middle. The pressure difference is different for each of these squeezes. Meaning this, like a voltage is pressure. So I'm going to measure the pressure on both sides of this. And you'll see here that there is a pressure difference, 2.5. 2.5 volts of pressure. Now, this one over here, they're squeezing really, really hard. So when they squeeze hard, there's going to be a big pressure. So what was 2.5 around the 5, this one here is going to be 7.5. It's fully 3 times bigger pressure. And if you look, this is 3 times bigger the resistance. So bigger resistance, bigger pressure difference. And over here, you'll see that this one's going to be in between. I bet it's 5, to be honest with you. Yep, there you go. So this was 5 volts. The other one was 7.5. And this one was 2.5. And you'll notice a relationship. This was one of the other questions in your activity. Do you notice a relationship between these voltages and your battery's voltage? And the answer is, yeah, they add up. 2.5 plus 5 is 7.5. 7.5 plus 7.5 is 15. The pressure is going to add up to the total pressure in the system. And think about this in terms of like a hose. Like if we had a hose and 3 people were kinking it, and you take the pressure drops of all of them, it's going to be the pressure of the battery. So big idea number 2 in a series circuit. The voltage adds to the voltage source. The current is the same everywhere, and the voltage adds. This is really important in a series circuit. This is, a very important, essential understanding in a series circuit. Now, something else about a series circuit, when you get to the resistance, you just add these resistors together. Like 15 plus 5 is 20. 20 plus 10 is 30. So the total resistance of this whole circuit is just add them all together. And if I were going to do Ohm's law, voltage being 15, resistance being 30, now you can see exactly why my current is 0.5. And we're going to get to that in another video, just really showing you how to break down a series and parallel quantitatively. But today, all we're going to be doing is talking about it from a concept standpoint. So concept number 1, the current is the same everywhere. No matter where I put this, the current is always the same, 0.5 amps. Big idea number 2, concept number 2, the voltage adds. The voltage around each of my objects, my loads, is going to add up to the total voltage. Now maybe you saw this in your activity, but when you take the voltage inside the same pipe, it's 0. What that's saying is there's 0 voltage difference. The voltage here is the same as the voltage that the pressure at that point in the pipe is the exact same as the pressure in this point of the pipe. So there's 0 difference. This voltage represents difference. That's why I need to have 2 of them. I need to sample the pressure before, and I need to sample the pressure after. And right now, there's 2.5 volts difference. I can sample it over here. That would be 10. There's 10 volts of pressure difference between this pipe and that pipe. Let's go on to a parallel that I whipped together on that circuit emulator. I've got 4 resistors, 10, 5, 10, and 30. And what makes a parallel circuit unique, it looks complicated, but really what it is the current has a choice. A series circuit, we talked about how there's only one pathway for the current to flow. Now, in a parallel circuit, there's more than one pathway. The electrons can travel through this branch, that branch, or the other. It's kind of like you when you're given a choice, like you're sitting in the gym and they say everybody can go. If everybody's going through this door, you don't want to go through that. You want to go through a door that's easiest to go through. And that's what's going on here. Current will always take the path of least resistance. So you'll look here, the one that has the least amount of resistance, more of these electrons are going to travel through there. And you can see it right now. And this brings us to concept number 1 with a parallel circuit. In a parallel circuit, the current is not the same. More current, 3 amps, is traveling through this branch. This one, I bet, is 1.5 because it's twice the amount of resistance. So if you have twice the resistance, half the current is going to throw. So here I've got current, I've got less current, still that same 1.5, and then here I got 0.5. All of the current through each of these is different. This was, I think, 1.5. That was 3. This current is going to add up. So 1.5 plus 1.5, that's 3 amps. 3 amps plus 3 amps is 6 amps, and 6 plus 0.5 is 6.5 amps. Look right here. This pipe has to supply the current for the entire circuit. So I bet if I mouse this over, I'm going to get 6.5. Sure enough, 6.5. Look down here. This is also a main vein. That's also going to give me 6.5 amps. Now, this piece right here, this has these 3 combined. So it's going to be 3 plus 1.5 plus 0.5. So this is going to say 5. See that? It's everything behind it. It's this water that's flowing plus this water plus this amount of water. All 3 of these added together is how much current is flowing through that branch right there. And one of the nice things about a parallel circuit is that you can turn one of these things off. Like this could just disappear altogether. And you'll notice that it doesn't turn off the whole circuit. It does turn off this branch though. Like if getting rid of this device, there's still a conductive pathway for this 10 ohm to work. There's still a conductive pathway through the 5, and there's still a conductive pathway. I don't have the total amount though that I used to have before. I have 5 instead of, I think it was 6.5 is what I started with. But big idea number 1 inside of a parallel circuit is that, number 1, it's a circuit with more than one pathway. Number 2, you just saw the current in each branch adds up to the total current. The current through each of these branches adds up to the total current. Now, what about the voltage? The voltage is going to be the same everywhere. It's exactly opposite of a series circuit, where in this one, the current was the same. Everywhere I put this, the current is the same, and then the voltage adds up to the total voltage. Here, the current adds up to the total current, so the current through each branch is the same. But now, the current through each branch adds up, but now the voltage is the same. So when I put my voltmeter here, I'm going to get 15 volts. When I put my voltmeter here, I'm also going to get 15 volts. When I put my voltmeter there, I get 15 volts of pressure. And when I put it there, they're all going to read 15 volts. Now, why is that? I put a couple of GIFs down here to kind of illustrate why this is. If you've ever played around with, this is called the Play-Doh Fun Factory. Back in the 80s, I had one of these, and they were a lot of fun. This individual is they're putting the same amount of pressure on every single one of these holes. And since every one of these holes is the same size, the same amount of Play-Doh flows through each one. Now imagine, if you would, if one of those holes was really, really big. Since there's the same amount of pressure, the one that's got the biggest hole is going to have way more Play-Doh going through it. And that's what's going on inside of this circuit right here. The same pressure exists on every single one of these devices. But one of these holes is way bigger and allows more of that water, that Play-Doh, to flow through it. So you're going to get more current through this device than you will that one. Current takes the path of least resistance. So each of these, the voltage, the pressure is the same. The amount of pressure on that is the same. The current adds up. Now here's something really unique about a parallel circuit. The more resistors I add, the more current flows, and that's counterintuitive. Like if you think about a series circuit here, the more resistors that you have, like here I've got half an amp. If I add a resistor to this, I'm going to slow the current down. I'll just grab a resistor here, put it in. So it went to 0.38. The more resistors I add, it's going to stifle more of the current. But over here, when I add a resistor, I'm actually adding in another hose. So adding in another resistor gives me a new pathway. Bear with me as I build this. Now I'm going to bring in my ammeter before I hook this up. And we saw before, I think this was 6.5 amps. If I add another device here, more current is going to flow when I let go now. It went to 8. Now, the more and more resistors that I add, the more devices that draw current, the more that this has to supply. Now, this is what's going on inside your room, any room inside of any building across the globe. Every time you plug something in, whatever is providing the electricity to the building has to provide more current just for that device. And we separate our rooms into circuits. So we protect the wires. If they have too much current flowing, the wires will melt inside your walls and they start a fire. And electrical fires used to be very common, and they kind of still are if you're not careful. Wires in our walls are rated for 15 amps. That's the typical consumer residential code in Platteville or wherever you are. So what we do to protect our buildings is we have what's called a circuit breaker. Back in the day, we used to have what's called a fuse. And so I'm going to set my fuse. I'll set my fuse to, like, let's say 9 amps. Typical fuses, 15 amps. Oh, shoot. Put my fuse in there, and that's all good because I only have 8 amps of current flowing. This has a little bit of resistance, so that's why we're getting a little bit less current. Now, if I add another one, if I add one more item to our room, plug in another hairdryer, plug in another something charging, I turn on another light, eventually that's going to be too much, and you're going to see too much current flows through that main trunk, and my fuse is going to break. Boop, there it goes, because I had more than what is allowed. So a circuit breaker. Down in your basement, it's a switch that if too much current flows, and they say right on it how much current that they can handle, and there's a little label saying what room is on that circuit. So you could go downstairs, flip that thing, and it'll turn off the electricity to that entire room, just like what happened here. All these things turned off. Back in the day, we used to have fuses, but then once your fuse blew, you had to get a new one. So you'd have to go to the hardware store and get another one. But if the hardware store, if this blew at night and you didn't have one, so you're just out of luck. So these are way nicer because you can just go downstairs, turn on a switch, and be back in business. But you got to remember, you just can't turn the switch back on. Like if I flip the switch, it's just going to flip again. I have to unplug that thing. So I got to ditch whatever was too much, and then I can flip my breaker again, and now it will work because I have less than what's recommended. So if a breaker ever goes in your house, it means you pulled too much current. So turn off something, either malfunctioned or you got too many things plugged in. Go unplug that thing, and then if you short the circuit, watch here, I'm providing no, and then boop, there it goes. And I'll go downstairs and I flip that thing, and it just keeps flipping because I haven't solved the actual problem, getting rid of that short circuit. Back in business. So I have one more circuit. This is a parallel. This is the exact same circuit. It's just a different configuration. The electrons can travel up, they can travel forward, and they're going to add up to the same. So 1.5 plus 3 plus 1.5 plus 6.5. So this is an identical circuit to what's over here. It's just drawn a different way. I'm giving, so here you can see a little bit easier the choice that the current has. It can go this way, it can go this way, it can go this way, or it can go that way. And you'll see that most of the current travels through there. In another video, we're going to talk about the qualitative. How do I actually predict how much current is flowing through each of these? And we'll get to that, but today we're just going to figure out the concepts. And the concepts are really big. In a parallel circuit, the current in each branch is going to add. The pressure on each of them is the same. The pressure on each of these holes, on each of these places for this hair to grow, the pressure is the same. The hole dictates how much Play-Doh flows. In a series circuit, it's the exact opposite. There's only one road for the water, only one pathway for this current to go. So a slowdown, one place slows down everything. The current is the same everywhere, but your pressure is going to add up to the total pressure. We'll see you next time, kids.